Okay, in this video, we will show you some examples of solution for diode circuit. So we go to the first example. So this is the first example. Okay, we consider a circuit which is a series parallel diode configuration. So the diode is connected with the resistor, and there is a series and also a parallel connection in the circuit. So the question is, by using the given diode IV characteristic curve in the next slide, determine the operating point for VDQ and IDQ. So the question is, what you need to do is you need to determine the what is VDQ. VDQ is the diode voltage, and IDQ is a diode current. This is IDQ. So the calculation need to be done using a characteristic curve. So this is a graphical. So this is a graphical approach. Okay. Before we move to the solution, I want all of you to take note that the symbol for the VD and ID, here we use VDQ, and then you use IDQ. So we put Q at the subscript. So the Q actually referring to the Q point. So this is the very common term used in the circuit analysis. What is Q point? Q point means the simply operating point. Q point is operating point. Okay, this is I want all of you to aware the concept of Q point. What is a Q point? Okay, and then next, how we can solve this circuit. Okay, we recall back on what we have learned in the graphical method. So in the graphical method, the circuit is quite simple. We have a resistor connected with the diode in series. So this is a very simple example that have been shown in our previous class, in our previous video. So what you need to do now is you need to simplify the circuit into this configuration. Okay, so how can it be done is you can use a Thevenin. Theorem. Okay, so this is the IV characteristic of the diode that we need to use. Okay, the first step is you need to simplify the circuit using the Thevenin. So you want to simplify this part, the part that that include 3 volt and include R1 and R2. So here you want to transform the circuit into something like this. Okay, this is 3 volt, and then this is, oh sorry, this is not 3 volt, it should be new Thevenin voltage. Okay, I write down the VThev, and this is new R Thevenin, and then this is 20 ohm, and this is 40 ohm, and we have this diode. Okay, so the detail for the detailed explanation on Thevenin theorem, you can revise, you can do the revision. This is, I think you have already learned this theorem in your circuit analysis. So the VThevenin, how we calculate the VThevenin? Okay, from this circuit, the VThevenin is actually the voltage across the R2. So you can use the voltage divider. So VThevenin is, use the voltage divider, Okay, voltage drop across the 200, and the total resistance is 200 plus 500. This is times 3. So this one you should get 0.857 volt. So this is V Thevenin. And how about the R Thevenin? So R Thevenin is, okay, when you trying to determine the R Thevenin, so you replace the DC source with the ground or short circuit, and then you from this point you see R1 and R2 are connected in parallel. So R Thevenin is the parallel of 500 parallel with 200, and the equation for the parallel is 500 times 200 divided by 500 plus 200. So this is equal to 142.857 ohm. Okay, so now you already you got the value for V Thevenin and R Thevenin. So next we can further simplify the circuit, okay, by adding R Thevenin plus 2 to 20 ohm plus 40 ohm. So okay, so we'll have a much simpler circuit, something like this. This is 0.857 volt. So this is R, the new R, and the new R is 142.857 plus 20 plus 40. So the answer is, this is 202.857 ohm. Okay, so you get this one. So this is much familiar circuit. Okay, after this, in order to solve the operating point, you want to use the graphical method. So you want to use a graphical method. Okay, for the graphical method, you need to draw the, we call it a load line. Okay, load line can be drawn by using the equation derived from the KVL. So you do the KVL. So start from here, we do the clockwise loop. So this is minus 0.857 plus, let's say this is IDQ, and then the resistance is 202.857, and then plus VD is equal to 0. So this, you get this load line equation. So next you need to draw this equation. Okay, how to draw the load line? So basically this equation is a linear equation. So this is a straight line. So you need only 2 points in the graph. So here, okay, what can be done is you make a table, VD and ID, and then you have two conditions because you want to have 2 points. The first condition is when VD is 0, and the second condition and when the ID is 0. So when VD is 0, the ID, based on this equation, based on this KVL, the ID should be equal to 0.857 over 200. 102.857. So this is equal to 4.22 milliampere. So this is a 4.22 milli. Okay, when ID is equal to 0, so VD is equal to ID is equal to 0, VD is equal to 0.857. So 0.857. Okay, so you already get 2 points. So next, you need to draw the load line. So the first point is when VD is 0, the current is 4.22. So 4.22, this is 4.1, this is 4.2. So should be around here. This is the point where VD is 0 and this is 4.22 milli. Okay, and then the second point is when ID is 0 and the VD is equal to 0.857. 0.857. So this is 0.85 here. So 57 is, I think let's say we put here. So this is 0.857 and the coordinate is 0.8570. Okay, so what you need to do is to draw the straight line connecting these 2 points. So connecting this 2 points. Okay. Okay. So because I'm using the hand drawing, so it's a bit difficult for me to draw the straight line. So I just try my best to draw the straight line. Let's say here, yeah, I use the dash line. Okay, you should draw the straight line. Draw the straight line. So this is load line. Once you got the load line, you identify the intersection. So actually I have try drawing the actual load line. The intersection should be around here. So we have this the intersecting point. So this is the solution. Okay, so the answer is, so you should get this is a VDQ. This is rough answer, the rough solution, and this is 0.8 milli is the IDQ. So the answer is, using the graphical method, the VDQ equal to 0.7 volt and IDQ equal to 0.8 milliampere. Okay, so this is how we solve the circuit using the graphical method. So the point here is when you are given circuit, so make sure you'll be able to simplify the circuit. Okay, until the circuit is in a form that a very simple form that have the one resistor and one diode connected in series. Okay, we have the sub question. So the first sub question, the second sub question is explain what happened to the Q point if RL is double. Okay, so in order to answer this question, you need to understand where the RL affect the solution. So the RL affect the solution in the load line, because here, okay, the RL is here, this is RL. Okay, RL will, when RL is double, the value for the R here, the R total also increase. So when the value of R increase, so what happen is the total will be more than 200 ohm, and then the current, the saturating point will be lesser. Okay, what is saturating point? This is saturating point. Saturating point is here. This is a saturating point. So when RL is double, the total resistance become bigger and the saturating point will decrease. So when the saturating point decrease, what happened to the Q point? To the Q point, you can imagine that when this line is the load line, the slope become lesser. The slope become lesser, so because it move towards downside, so the Q point becomes smaller. Yeah, the Q point becomes smaller. Okay, so the answer is the IDQ and VDQ become smaller because the load line, the slope becomes smaller, and then the Q point shifted toward the left side. The Q point shifted toward the left side, and IDQ, so VDQ will shifted toward the left side also. Okay, if I use this one, this is the ID versus VD. Let's say this is a diode. This is the first load line, first one, and let's say what happened if after load line will become something like this. This is after, so you can see what happened is the Q point 1 become Q point 2, means that the VDQ decrease. Okay, this is moving towards, shifted toward left side, as well as IDQ also decrease, shifted to the lower value of current. So this is the answer. Okay, next, what happened to the Q point if the ambient temperature increase? So in order to answer this question, you need to understand the effect of temperature to the diode. So when the temperature increase, the diode IV characteristic will be affected. So what happened is, okay, we consider the fault bias. So let's say this is a before, this is ID versus VD. Okay, when temperature increase, the majority electron carrier inside the P junction will have higher energy, and there will be more free electron because more electron is released, being generated from the valence electron. So there's more higher possibility for the electron to move across the p-n junction. So in the ID-VD characteristic means that the sudden increase of the current will occurs at much lesser voltage. So become something like this. So this is after temperature increase. So this is before and after. You see the knee voltage shifted at the lower value. So what happened? Let's say we draw the load line. Okay, we draw the load line. So the Q point, the difference of the Q point. Okay, the VDQ smaller, but the IDQ become higher. Okay, so this is the answer. Okay, so next we go to the example number 2. Okay, example number 2, the same circuit, but now we want to use a equivalent model. We use a practical model. Okay, when you're using the equivalent circuit, so first thing you need to do, you need to be able to identify whether the diode is in forward or reverse bias. So the first question is it forward bias or is it reverse bias? Okay, is it forward bias or is it reverse bias? Okay, so because since we have only one DC source, so this is high possibility that the current should be moving clockwise here. So at the first, I think this possibility that the diode is on. There should be much higher voltage at the anode compared to the cathode. So this is a forward bias. So we assume this is a forward bias. Okay. So in a practical model, if the diode is in forward bias, we replace the diode. So this is diode. We replace the diode with a DC source. Okay, because this is a silicon and the new voltage is 0.7, so the value of the DC source is 0.7 volt. Okay, so we can redraw the circuit. So this is a this is 3 volt, this is 500 ohm, 20 ohm, this is 200 ohm, 40 ohm, and then this is 0.7 volt. Okay, so next, that you have many approach to solve this circuit. You can use the previous. You can apply the previous approach where we simplify the circuit using the Thevenin theorem. This is much easier. But now I want to show you another type of solution, another approach, how it can be done. Okay, but I think the easier one is using the Thevenin. But now I just show you how we can use another approach. We use a mesh analysis. So how to use the mesh analysis? Okay, you identify the loop. Let's say we use this loop. This is the first loop, and then this is current I1, and this is a second loop. The current is I2. Okay. So first, for the mesh loop, mesh analysis, you need to do the KVL for the loop, for every loop. The first is the loop I1. So we start with at the 3 volt. So the 3 volt is -3. And then we have the 500 plus. So the current at the 500 is I1. So we have the I1 500. And then this is 200. So the 200, we have two current, I1 and I2. Okay. So now we consider the clockwise direction. So this is I1 minus I2 times 200. So and then next we have completed the loop. So this is equal to 0. So you can simplify this one and you should get -3 plus I1, this is 700, and minus I2 200. This is equation 1. For the loop I2, so let's say you start here. This is a positive I2. 20, and then you have the positive I2 40. Okay, now this is the clockwise direction, and then this is a DC source, and this is a positive terminal. So this is entering the positive, so this is positive. So this is positive 0.7, and then this one at 200, because we consider the clockwise, so this is I2 minus I1 200 equal to 0. Okay, when you solve this, you want to simplify this KVL. What you should get is 0.7 minus I1 200, and then plus I2 220 equal to 0. This is equation number 2. Okay, so you need to, you have equation 1, equation 2, you solve the both equation 1 and 2. Okay, this is a solution of simultaneous equation. Make sure that you can use your calculator to solve this simultaneous equation, because this part is not really considered for your when for the marks. This calculation is not considered. It's not considered for the marking, the marks. But anyway, make sure that you'll be able to use your calculator to get the answer. Okay, for simultaneous equation. So the solution is I1 is equal to 0.00456, which is equal to 4.561 milliampere, and then I2 is equal to 0.000965 equal to 0.6965 milliampere. Okay, so our question is we want to calculate the ID. Okay, we want to create the ID. So the ID is equal to I2, which is 0.965 milliampere. So this is the final answer. Okay, if you compare with the one that used the graphical method, last time we get around 0.8 milliampere, but now we get 0.965 milliampere. So we have the slight difference between using the equivalent model and the graphical method. Okay. We go to our last example. So this is the circuit that consists of two diodes, D1 and D2, and both are silicon type. So both are silicon type. So means that the knee voltage or the voltage barrier is 0.7 volt. Okay, and then this the question requests you to use the practical model. So means that you need to replace this diode with a practical model. And the question is, identify if diode 1 and diode 2 is on or off. Show your calculation to justify your answer. So when you use the practical model, or use the equivalent model, so in this approach, you want to replace the diode with certain model. So this certain model is they have the condition. For example, whether you need to able to identify whether the diode is forward bias or reverse bias. So this is the first things that you need to decide, forward bias or reverse bias. Okay, so in this solution, so first let's assume all the diode is in forward bias. Okay, when all diode is forward bias, okay, so the diode can be replaced with a DC source, and then the value of DC source is 0.7 volt because of the second type. So you can redraw the circuit. This is 6 volt, and you have 12 kilo ohm, and then you have this one is 0.7 connected in series with 6 kilo ohm. This is 0.7 volt, and then next you have 2 kilo ohm, and then this is 0.7, this is 2 volt, this is okay, this is 1 milliampere current source, this is 0.7 volt, this is 2 volt, and this is 4 kilo ohm. So you replace the D1 and D2 with the DC source. Okay, next we already replaced the diode with the DC source. Okay, this is when we assume that diode is in a forward bias. So next we need to do is we want to get our final analysis is we want to get this diode current. Let's say this is ID1 and this is ID2. Okay, take note that the direction that I draw like this, I draw the direction of ID1 as if the diode is in forward bias, which is in on condition. Same goes with ID2. ID2 current direction is as if the diode is in on condition. So in our analysis, we want to see whether this ID1 is positive or negative. If positive, it follow the drawn direction. If negative, it is opposite of the direction. Okay, how we can do the analysis? We do the mesh analysis. So this is I1, this is I2. We do the mesh analysis. Okay, so first this is loop I1. The loop I1 starting from the 6 volt. So this is minus 6 plus, this is 12 kilo ohm, only one current. This is I1 12K, and then we go to the 0.7. 0.7 is entering the positive, so this is positive 0.7, and then we have the 6 kilo ohm. 6 kilo ohm, there are two current, I1 and I2. So this is plus I1 minus I2 times 6 kilo equal to 0. So you simplify the equation, you get minus 5.3 plus I1 18K minus I2 6K equal to 0. Okay, next we do the loop 2, loop I2. Okay, loop I2, let's say we start from okay, let's start with this 0.7, the diode one. So this is the current is exiting from the positive, so this is negative 0.7, negative 0.7, and then plus I2 2 kilo. Okay, then next we have this 0.7, this diode. Okay, this is also exiting the positive, so this is also negative 0.7. Okay, now this is entering the positive, so this is positive 2. Okay, for the 4K, there is two current, I2 and the current from the current source, 1 milliampere. So this is I2 plus 1 milli times 4K, and then last one we have the 6K. This is plus I2 minus I1, 6K equal to 0. So you do all the simplification, simplify this equation. Lastly, you should get 4.6 minus I1 6K plus I2 12K equal to 0. So this is equation number 1 and this is equation number 2. You solve the equation number 1 and number 2, you should get this answer. So I1 is equal to 0.2 milliampere and I2 is equal to minus 0.28 milliampere. Okay, this is the solution for the spontaneous equation. Okay, but now next we get the actual diode current. So ID1 here, okay, ID1 here is moving towards the downward. So this is I1 minus I2. So this is 0.2 minus minus, so this is plus, is equal to 0.4. So 4.48 milliampere. Okay, so this is a positive, means that it follow the drawn direction. So this is on. Diode 1 is on. Okay, how about ID2? ID2 is in this direction. Okay, see this direction. So this is minus I2 because it is opposite of the I2, and then this is also minus 1 milli. So you get the minus 1 milli minus 0.28. So it should be minus 0.72 milliampere. So the polarity of the current is minus, negative. So means that the actual direction is opposite of the drawn direction. So means that our assumption is incorrect or wrong. So the diode is off. So the answer is diode 1 is on and diode 2 is off.